So, hello everyone, this is lecture 29 for the quantum mechanics. In the last lecture, we have studied about the Einstein equation and the equation of motion. So, today we will start the application of quantum mechanics part. So, here we will study about the single particle system, means the Schrodinger equations is very hard to solve for the multi particle system. That's why we will solve for a single particle. And here we will study about the potential step, potential barrier, particle in a box, harmonic oscillator, and the Dirac delta potential. So when I discussed the syllabus with you in the starting, so I told you about this. So this is what we're going to study. So in all the cases, what will be the procedure to solve? So the procedure will be, first we will write the Hamiltonian for the system. In Hamiltonian, we will write the kinetic energy and the potential energy term. So this will remain same for a single particle, but the potential will change for the different kind of system, is for the potential step and the potential barrier. So this part will change. So we need to first write the Hamiltonian. Then we will solve the time independent Schrodinger equation. Means we will find the eigenvalues. Means if Hamiltonian operator is given, from here we will find all the eigenstates and the eigenvalues. See, this will be some matrix, so we can solve that for the eigenstates and the eigenvalues. So to find complete set of eigenstates and corresponding eigenvalues, so we'll solve this. Then if it is means though two eigenstates means 22 matrix, then we will get two eigenstates and the two eigenvalues. If it is 3 to 3 matrix, then we'll get three eigenstates and the three eigenvalues. And see, as I told you that this potential can change. So just like for a oscillator system, harmonic oscillator, you will get this kind of potential graph, and this is your potential kx square by 2. And for a potential valve, you will get this kind of potential, means it is 0 for it and v naught for this. So that's how your potential will change for the different systems. Then you will solve the time independent Schrodinger equation to find the eigenstates and the eigenvalues. When you have the eigenstates and the eigenvalues, you can write the time independent wave function, and the linear time means this is a linear equation, linearly independent. So psi x will be ci phi ix. So it will be phi 1, phi 2, phi 3 depending on the eigenstates. So you can write this equation after this. Then we can write the time dependent wave function. Means if we know the time independent, then we can just write this. We know this, how to find this. We already solved many questions based on this. Now let's start. First we will study what is the meaning of bound and the unbound states. So I already discussed these things in the classical physics also. So this will remain the same, but the only difference will be that here in the bound state we will get the discrete energy states. So see, this is your potential energy curve, and this is like potential is high here, low here, and this is most high here. So if the particle has energy in this particular area, then at this point its potential energy will be equal to means this total energy, and kinetic energy will be 0, means particle can't move above this. So these will be your turning points, means particle will oscillate between this. So this is called the bound motion, and here also it will bound, here also it will be bound. But when it is goes upside this, so then the particle will turn from this and go to infinity. So that will be unbound motion. So that is the basic definition. And the bound state, the particle can have only discrete energy states, means first 2 and 3. So it will be discrete spectrum. So in the bound states occur whenever the particle can't move to infinity. So here it will be bound and it can't move to infinity. That's why we call it as bound system. So if the potential is here, we call it as V minimum and it is V1. So energy will be between V minimum and Vn to get the bound state. In this case, motion of the particle is bound between the classical turning points x1 and x2. So as I told you. And the states corresponding to the energy range V minimum and Vn are called the bound states. So whatever states the particle can take between this V minimum and V1 is called the bound states. Now the energy spectrum of the bound states are discrete. So as I told you, that is the difference. Now see how you can imagine this bound state. We can just say that if there is a cylinder at potential V naught, and here is also a cylinder at potential V naught, and this cylindrical structure is at the 0 volt. So potential curve is something like this. So if some positive particle or proton will be released here, so it will be oscillating between these. It will be released like this, so it will be oscillating between this state. So this will be your bound state because it can't move outside this. And also you can imagine you have some two positive plates, charge plates, and the proton is released here, so it will be repelled by this, and it will reach here, it will repel by this, so it will be means bound to oscillate here. So that is the bound state. And there is one more thing about the wave function, that wave function collapse or the vanish at the boundaries. So there will be some nodes. So let's study about the nodes. In all the 1D problems, the energy levels are discrete and not degenerate. Now the sin x, this is your wave function of 1D bound state, has n nodes. Means if for the harmonic oscillator we know n equal to 0 is the ground states. For that there will be n times it will vanish, means wave function will vanish n times, there will be n nodes. But if the ground state starting from n equal to 1, then there will be n minus 1 nodes. So you must remember this thing, particle in a box, like we will have the first ground state at n equal to 1. So we'll study this in detail. Just you need to remember that how many nodes will be there for different cases, and nodes means the wave function will vanish. Now there is unbound state. So as I told you, then when particle has energy greater than this v1, then it will be means turned from here and it will go to infinity. So this is unbound motion. So this is called the unbound motion. And here the particle can have the continuous energy, means not discrete. So when energy between v1 and v1 and this v2, then particle will go from this point to the minus infinity. So particle can move from between x equal to x3 to x equal to minus infinity, and the system will be unbound system and energy spectrum will be continuous. So you must remember these terms. When E is greater than V2, when E is greater than this particular potential, then it can go to the minus infinity to plus infinity. So that is the motion after V2. That is also unbound, and energy spectrum will be continuous for that also. So you must remember these points, that what is continuous and what is not discrete, and what is bound and what is unbound. So you must remember all these terms. And what we will study is, let me give you a summary for that. Then potential step will be something like this, means particle is there and there will be some potential. So it will means turn from here. So it will be your unbound motion, and that is called the potential step, something like that. And potential barrier will be something like this. So these both are the example of unbound motion. The potential step, we will see this. But the four things we will study, that is the infinite potential valve and the finite potential valve. Then we will see the harmonic oscillator, and we will see for the hydrogen atom. So these all are the bound states. So we'll study all these six in detail. So that's it for today. In the next lecture, we will see about them. We'll start with the potential step. So thank you everyone.